Thank you very much. Thank you for the organization also. My name is Macias from Grafana Labs, and today I will introduce you Grafana Beyla, the product we are working on, and how it can provide metrics and traces from your application using eBPF and export them to Prometheus. So imagine a legacy application which is not instrumented, and you just want to get some metrics from it. So in the best case, this is a very simplistic graph, but if your application uses a runtime like JVM or .NET, you can insert an agent, and with a bit of extra configuration, you can push or pull your metrics from Prometheus. But what happens with compiled languages like Go, Rust, C? If you want to instrument it, you need to get your code and add some instrumentation points. Then you rebuild it, you get your instrumented application, and it's ready to work. But with legacy applications, old code, it's not always easy, because you maybe don't have the time or the resources, or for example, you are using an old version of the compiler or the runtimes, and you don't have source level compatibility with the newest, latest versions of the instrumentation libraries. So Beyla comes here to fill this gap, and by means of eBPF is able to attach to some events of either the operating system or also your application, as well as its runtime and libraries, and provide the metrics for you without requiring to modify your application. You just need to deploy it with them. eBPF, it's a fancy word. The first time I heard it is eBPF, what? So let me first demystify a bit, talking about what is not eBPF. It's not magic. It's not something you can say, okay, I have a query language, please, eBPF, show me all the information I want, and format it to me so I can parse it automatically. It's not something like that. What's more eBPF? For me, eBPF looks like more a set of peepholes you have in the kernel, or you can set in your application. And once you look into them, you can see the matrix there. Fortunately, if you know where are you looking into, you know how the binary data is structured and organized, and then you can extract it. So eBPF, extended Berkeley packet filter, but someone noticed me that it is not. It was the original name. Now it's eBPF. Doesn't have anything to do neither with Berkeley nor packet filters. It's a just-in-time virtual machine at the Linux kernel that allows you to hook some proof programs in multiple events of the kernels, in the libraries, in the user space programs, even in the network stack. So let's you see, even modify the memory at the runtime. But you need to know, as I mentioned, how the memory is organized at the binary level. That means that what you look for, from eBPF will be different according to the language, the compiler, or the architecture. That means the argument, the data structure, the local variables, the return values. More or less, all the mainly languages follow similar conventions, but not all the languages or the compiler versions follow the same conventions in the way they structure this binary data. So you need to know what you're looking and how these programs you are inspecting are compiled. This is an example. Imagine we want to trace each new TCP connection in eBPF. So we first need to know that this TCP connection is handled through a given function in the kernel. So once we know which is this function, which arguments it takes, which return values it has, you can write the BPF probes for it. BPF probes are usually written in C. I've seen some libraries that allow do it in Rust, but the common language is C. And you need to compile it not for your native architecture, but for the BPF instruction set. So if you want to monitor that, you first need to deploy in the user space as a regular, as a process in native code, the monitoring process, the process that will load these BPF probes. So the compiled language or the compiled binary is inside this native, as a data structure is inside this native monitor. So it will, through some system calls, it will load it into the kernel. I will say, okay, please attach this BPF probe to this kernel event, like is the TCP connect. So this BPF probe then will be executed every time the TCP connect function is executed, and will communicate with with Beyla, in that case, with the monitor process, through eBPF maps. That is, hash maps, ring buffers, etc. And then the Beyla, in that case, gets all this information, processes it, and then is able to forward it. The advantages of eBPF is that it is fast. It is just-in-time compilation, so every probe is executed at the native speed. It is stable. That means that programs are pre-verified before loading. It prevents unallowed memory accesses. It prevents, sorry, this is a typo, it prevents infinite loops. So you can safely load it without hanging your kernel. And even if it is clean, if, for example, your monitor program crashed, all the probes will be automatically cleaned up, so you won't pollute your kernel. It has some disadvantages. It is hard to debug. A part of printfs into a file in the kernel. I don't know any other alternatives. As I mentioned before, your probes are often dependent on the implementation details, whether the arguments are passed in the stack versus the register, the architecture, language, compiler conversions, big endian versus little endian, etc. Some changes in the inspected APIs also can break your code. If they push another version of the executable with different APIs, it can break your code. For example, with Go 1.16 to Go 1.17, they changed the way the arguments were passed. It used registers, then it used the stack, or vice versa, I don't remember, and that made that any new Go program will not be instrumentable with the old eBPF code. Another issue is that you need at least sysadmin privileges, because you need to do some system calls to load this code into the kernel. Let's talk about Grafana Beyla. Once we have demystified eBPF and agree that it's not magic, let's show the magic of Beyla. Joking. So Grafana Beyla allows or automatically instruments your services and clients and provides metrics and traces for them. It is able to instrument Go executables, inserting probes into the user code. Now we are able to instrument HTTP, HTTPS, and gRPC services. And for other languages, using the kernel, hooks probes into the kernel, we are able to instrument HTTP for, I'd say, any language we've tried, and HTTPS for almost every language. I'd say all but Java. At some point, more protocols and languages are going to come. Grafana exports the data as red metrics. This is request, errors, and duration for every HTTP request, as it is able to export either as Prometheus and OpenTelemetry metrics, and also it's able to export this information as OpenTelemetry traces. This is the current supported Prometheus metrics. They follow some common convention you might have seen, for example, in the previous talk. And it also exports internal performance counters, which are not very relevant, but in case you want to see how Beyla is working. So let's do a quick demo. I have an Nginx server. This Nginx doesn't bundle any kind of plugin or special configuration. I just did apt install Nginx. Then I configured it for HTTPS to communicate via HTTPS, and I loaded just a web page template I found in the internet just to see how it works. So let's start Beyla in this host, and let's see how it is instrumented. We try to put a lot of emphasis in the adoption easiness. So you only need 2 properties to start running Beyla. One property is to tell Beyla which executable you need to instrument. You have 2 options. The first option is by the name of the executable, or maybe it's easier by the open port. So I will tell Beyla that I will ask Beyla to instrument the executable that owns this port. Then you need a way to tell Beyla how to export the metrics and the traces. So for the metrics, we will use, of course, Prometheus. So I will tell Beyla to expose a Prometheus endpoint in this port. And just for debugging purposes, I will tell Beyla also to print the traces in the standard output. So I run with these properties, I run Beyla. Okay, we can see these errors you see. Don't worry about them. They are not actually errors. But let me clean the buffer. So I will just start interacting with this application. Okay, you can see here it printed 2 traces. You can see, for example, the duration of the trace. This is the return code, the method. This is the path, and then the source and the destination. You can see also, if it were a post request, you will see also the size of the request, and here you can see the executable that is doing it. So let me just play a bit more with it, and we should see some other metrics. Let me reload. Okay, you will see. So let me just, in this metrics endpoint, okay, this is the demo. Okay, it should show some. This is the demo effect. Okay, that's super cool. Let me just try to, maybe since this is a virtual machine, let me just try. Okay. Okay, that is probably because I did a typo. Yeah, sorry. This is not Beyla Prometheus metrics. This is Beyla Prometheus port. At least you see that I'm not faking the demo. Okay, so let me play a bit more. And you will see here, then, okay, you can see here the Prometheus. This is with the simplest configuration. You see some labels, but let me show some extra configuration you can provide. For example, you can provide a YAML file with all this information. You can see how to export the metrics. You can also see how to specify how to export the internal metrics, just to know how Beyla is performing. And also, it allows report the HTTP target. But if you want to avoid cardinality explosion, for example, you can group those traces or those targets into common roots. For example, I say that anything that is any image, just please report it as this, not the whole image, so you don't get an explosion of labels. So let me run Beyla here with this config parameter. Let me just play a bit more and reload. And you will see Beyla with the new extra attributes like the root, for example. You can see here that, for example, in that case, the roots that are recognized are reported as roots, and the others that are not in the list I sent are reported as normal HTTP targets. You can configure. If you want to, instead of reporting the whole path, you can just report or not report it, or report an asterisk or whatever to avoid cardinality explosion. So thank you for your attention. That was the demo. I'd like to conclude that, okay, Beyla doesn't provide the same granularity as instrumenting manually your application, but it provides you an initial point or an initial step to get instrumentation without having to deal with the complexity of integrating the agent or the libraries into your code. So thank you for your attention. If you have any question.
Finally, people have instantly questions.
I would like to ask you if Beyla is running only on bare metal. I mean, this kernel module needs to run on a bare metal, or it can also run in a containerized environment. And if it does, then what is the impact of Beyla, for example, in a containerized environment? What's the performance impact, for example, in a bare metal server that acts like a node in a cluster? Thank you.
Thank you for your question. Good questions. Beyla can run in containers, but either Docker container or Kubernetes pods. But they need to be privileged containers. And also, they need to share the PID namespace, the process ID namespace of the container they are instrumenting. With respect to the performance, I don't want to provide you anything official because we already don't have it. But our initial calculations is that is low. I wouldn't say low, okay, but as a comparative measurement, for example, there are some interested people using languages like Python or Ruby because Beyla, the overhead of Beyla is lower than some libraries that are written in non-native languages. But the official performance impact will need to be released because we at the moment have only very synthetic performance benchmarks. You mean a ping service with millions of requests per second, and then the measurements are not realistic.
Okay.
Hi, thank you for the very nice presentation. My question is, how far can you push the boundaries of automatic instrumentation? So you have shown that you can instrument communication primitives like HTTP, HTTPS, Google RPC. What about different functions like memory allocation, free, etc.? Is there any plan, and how far can you go?
Yeah, we believe, but I don't want to give any. At the moment, we are researching on that, but it is possible as long as you know where to hook. For example, you can instrument the code runtime, know the garbage collections, or get other runtime metrics. You just need to know where to hook, and it's not as simple as just hooking to a given event. Maybe you need to hook into different layers and then match the data. To be honest, I thought the boundaries were much tighter than we are finally discovering. So as long as we keep learning about eBPF or learning about the systems, we see that the boundaries grow. Yeah, we with eBPF, and I hope so at some point Beyla can do it, you can get this kind of metrics, extra protocols like SQL, Kafka, and so on, but also get information about the runtimes.
Great.
Thank you for your presentation. I do have two questions. So the first one is, can one process for Beyla instrument two or more applications at the same time, or is it only just as a sidecar to the application?
Currently is one Beyla, one process, despite the Beyla has a system mode in which it's able to instrument everything. But we are currently working on being able to instrument multiple processes with one Beyla. It is in our roadmap. We are, if you join this GitHub site, you will see the current status of the different tasks. Yeah.
Thank you. And the second one, why not Java? Or can it instrument JVM and Java processes?
We can instrument HTTP on Java, and we can instrument multiple parts of the JVM. But in the case of SSL, of TLS, Java uses its own library implemented in Java for TLS. So instrumenting with eBPF code from the Java virtual machine is really, really complex because you get just-in-time compilations or you can get interpreted execution. So you need to listen to multiple events. It is part of our research. So the Java virtual machine will also provide some extra hooks. So maybe you can listen to these compilation events and so on, and at some point you can. But this is a lot of work, and at the moment we haven't had the time to work on it.
Last question up there. We need to make it quick.
Hi, I'd like to ask, since it's instrumenting HTTP metrics, does it, and traces for HTTP, does it also support context propagation injection?
Very, very good question. At the moment, we are able to acquire the context from the parent call and then attach it to the metrics. The big difficulty comes how to propagate if your instrumented service then invokes another service, how to propagate the contacts to the child traces. This is very, very difficult because you need to work with pre-allocated memory. You need to also insert those traces for example, in a Go server, you need to insert this trace into a Go map, which is managed by the Go memory manager. So this becomes an unsafe operation because you could expose some data, and also because in the later version of the Linux kernel, you cannot write the user space memory. You cannot modify it unless you enable an unsafe kernel feature, but by default you won't be able. So this is something we're also working on. We did half the path, which is get the context from the parent, but translate it. Oh, sorry. Yeah, it's more complex.
Okay. Thank you so much for the talk, and yeah, I guess you're around for questions.
Thank you very much.